Hi everyone, this video serves to go through the H2 chemistry tutorial on solubility equilibria from question 4 onwards for the 2025 JC2 cohort. But before we start with question 4, there are some fundamental skills which you must be familiar with from questions 1, 2 and 3. For question 1, you need to know how to write the correct KSP expression for a sparingly soluble salt. And for questions 2 and 3, you need to know how to calculate the KSP from solubility and vice versa to calculate the solubility from the KSP. So now let's look at question 4. We have an acidified solution which contains 3 salts, calcium chloride, iron 2 chloride, and manganese 2 chloride, each of concentration 0.1 mole per dm cube. We bubble carbon dioxide into the solution until it becomes saturated with carbon dioxide, and eventually there is a carbonate ion concentration of 1 times 10 to the power of negative 9 mole per dm cube. So your first question might be, how come I bubble carbon dioxide into the solution? It leads to formation of carbonate ions. And this is because, firstly, when I bubble carbon dioxide into solution, it reacts with water to give me carbonic acid, H2CO3. H2CO3, you can tell from the formula that this is actually a dibasic acid. So H2CO3 will first dissociate to give you H plus ions and HCO3 minus ions. But these HCO3 minus ions themselves are also mildly acidic and can further dissociate to give you H plus and CO3 2 minus ions. And by Le Chatelier's principle, it predicts that when there is a significant concentration of acid, it is going to shift the positions of both equilibria to the left, thus giving us a low concentration of carbonate ions, which is important because if your carbonate ion concentration is too high, all the carbonates, which is calcium, iron, and manganese, will precipitate out at the same time. So now let's look at the fundamental concepts behind this question, which is testing you on your knowledge of the condition for precipitation to occur. But before that, we need to look at what is called the ionic product, or IP, of a sparingly soluble salt. The IP is following the same expression as the KSP, with the very major exception that KSP refers strictly to saturated solutions, but IP may be under situations where the salt is not saturated. And for a precipitate to form, the IP of the sparingly soluble salt must exceed the KSP. So for each of the carbonates, they have the same type of formula. We can write their IP expression as the concentration of M2 plus multiplied by the concentration of carbonate ions. Question has given you that the concentration of M2 plus ions is 0.1 mole per dm cube. Concentration of carbonate ions 1 times 10 to the power negative 9. So the IP for all 3 carbonates is 1 times 10 to the power negative 10 mole squared dm power negative 6. And this value exceeds the KSP value for iron 2 carbonate and manganese carbonate, which implies that you will only precipitate out iron 2 carbonate and manganese carbonate. Since the IP value is smaller than the KSP value for calcium carbonate will not precipitate out. With that, let's look at question 5. Predict whether precipitation will occur when 50 cm³ of 0.01 mole per dm cube of magnesium nitrate is added to 200 cm³ of 0.001 mole per dm cube aqueous sodium hydroxide, given the KSP value of magnesium hydroxide. Okay, so to solve this question, I need the IP of magnesium hydroxide. So before that, I'll need the concentration of both magnesium ions and hydroxide ions after mixing, which allows me to calculate IP. And secondly, I need to write the correct IP or KSP expression for magnesium hydroxide. So when the amount of magnesium ions is given by the volume multiplied by the concentration, which is this amount, and the amount of hydroxide ions will be 0.2 times 0.001, which will give you this amount. After mixing, the total volume is 50 cm cube plus 200 cm cube, which will give you 0.250 dm cube. Next, I'll write the the IP expression for magnesium hydroxide and substitute in the new concentrations of both ions, which will be the amount divided by the new volume after mixing. I can then press calculator and you'll find that the IP is 1.28 times 10 to the power of negative 9 mole cube dm power negative 9, which exceeds the KSP value for magnesium hydroxide, and thus we'll predict that a precipitation will occur. Next, we're going to look at question 6. We have 1 dm cube of a solution containing equal concentration of both chloride and iodide ions, and we are adding solid silver nitrate slowly to the solution. Given the solubility product values for AgCl and AgI, show that AgI precipitates before AgCl. So firstly, the word show in the question tells you that you must present relevant workings or calculations to solve this question. So remember, to precipitate AgCl, the IP must be greater than or equal to KSP. So the minimum concentration of silver ions to precipitate AgCl will be the KSP divided by the concentration of chloride ions, which will be 1.8 times 10 to the power of negative 8 mole per dm cube. Whereas to precipitate AgI, the minimum concentration of silver ions will be KSP divided by concentration of iodide ions, will give you 8.5 times 10 to the power of negative 15 mole per dm cube. So since a lower concentration of silver ions is needed to induce the precipitation of AgI, AgI is going to precipitate first. Next, part B. What is the concentration of silver ions in the solution for maximum separation of two anions, where the maximum amount of AgI is precipitated without precipitating AgCl? So for us to precipitate AgI but not AgCl, the concentration of silver ions must be such that the IP, the ionic product of AgCl, does not exceed its KSP. So since KSP is the concentration of silver ions multiplied by concentration of chloride ions, so the concentration of silver ions to achieve a situation where IP is equals to KSP will just be KSP divided by chloride ion concentration, which will be 1.8 times 10 to the power of negative 8 mole per dm cube. Next, part C. What is the concentration of iodide ions remaining in solution when AgCl begins to precipitate? So over here, the solubility product of AgI is the concentration of Ag plus multiplied by concentration of I minus. So the concentration of I minus, where AgI does not precipitate, is KSP divided by the silver ion concentration which you obtained in part B, which would be the 8.5 times 10 to the power negative 17, the KSP of AgI, divided by the silver ion concentration in part B, which is 1.8 times 10 to the power negative 8 mole per dm cube. So this tells us that even after AgI is precipitated and AgCl is going to precipitate, that there is this concentration of iodide ions present in solution. And this, if you notice, is much lower than the concentration of chloride ions that is present in the solution, such that when the silver ion concentration reaches the level in B, the IP will still be smaller than KSP for AGI. Thus, AGI will no longer precipitate, but IP is equals to KSP for AgCl, which means that AgCl will soon begin to precipitate. And this also tells us that we can never fully remove any ion in aqueous solution via precipitation. There will always be a very, very small concentration of the ion left behind in the aqueous solution. Finally, part D, separation is considered effective when less than 1% of the anion remains in solution. So to find the percentage of iodide ions remaining, we will take the final concentration over initial concentration times 100%, which will be 4.72 times 10 to the power negative 9 over 0.01 times 100%, which will be 4.72 times 10 to the power negative 5%. So this value tells us that virtually all of the iodide ions have been removed by precipitation with silver ions. There is only a very, very low concentration or very, very low proportion of iodide ions left. And since this value is much less than 1%, we can conclude that the separation was effective. Next, we're going to look at question 7. At 298 kelvins, the equilibrium concentration of iodide ions in a saturated solution of PbI2 is this value, and use this to calculate the KSP of PbI2 at 298 K. So firstly, we're going to start with the dissociation equilibrium of PbI2, which is as shown. Next, since it's given that the iodide ion concentration in this solution is 2.7 times 10 to the power negative 3, so by stoichiometry, the concentration of lead-2 ions is half of this, will be 1.35 times 10 to the power negative 3 mole per dm cube. And then writing the KSP expression, we can substitute in these values into the KSP expression. And then we press calculator. The KSP value for lead-2 iodide is 9.84 times 10 to the power negative 9 mole cube dm to the power of negative 9. Next, part B, 1. At 298 K, calculate the solubility of PbI2 in pure water. So in this, the solubility of PbI2 in pure water would just be the concentration of lead-2 ions because the two species are in a 1:1 mole ratio. So the solubility of PbI2 will be 1.35 times 10 to the power negative 3 mole per dm cube. Next, calculate the solubility of lead-2 iodide in 0.20 mole per dm cube lead-2 nitrate solution. Firstly, please note that lead-2 nitrate is a very soluble salt which undergoes complete dissolution or dissociation in water. What this means is that in a 0.20 mole per dm cube lead-2 nitrate solution, the concentration of Pb2 plus ions will also be 0.20 mole per dm cube. So letting the solubility of PbI2 be x mole per dm cube, at equilibrium, the concentration of Pb2 plus in this solution, which contains PbI2 and PbNO32, the concentration of Pb2 plus ions is 0.20 plus x, because there are two sources that contribute to the Pb2 plus, which is 0.2 mole per dm cube from the lead-2 nitrate and x from the PbI2. For iodide ions, it will just be 2x because there are no other sources that contribute to the iodide ions. We can substitute these into the KSP expression. So KSP equals to 0.2 plus x multiplied by 2x squared equals to 9.84 times 10 to the power of negative 9. And this KSP value is the same because ultimately KSP is a type of equilibrium constant, and equilibrium constants are only affected by temperature. Now we can expand this out into a cubic equation, but we don't need to do that. So firstly, we've already noted that PbI2 is sparingly soluble, PbNO32 is much more soluble than that. So the contribution of the Pb2 plus ion concentration in this solution, which is 0.20 plus X, the 0.20 will make up the vast majority of the Pb2 plus ions in the solution because X is very, very much smaller than 0.2. So we can approximate that 0.20 plus X is approximately the same as 0.20, and then our equation will become 0.20 multiplied by 4x squared equals to 9.84 times 10 to the power of negative 9. And you solve for x will be 1.11 times 10 to the power of negative 4 mole per dm cube. And even if you didn't approximate, you solve the cubic equation, you will still get the same value of x, which proves that our initial assumption or our initial approximation was valid. And you will notice that in 0.2 mole per dm cube lead-2 nitrate solution, the solubility of lead-2 iodide has been significantly decreased compared to in pure water. And when we do H2 chemistry, there is no need for you to solve quadratic equation and cubic equations beyond simple ones such as x squared equals to a and x cubed equals to b. So this is an illustration of what we call the common ion effect. Common ion effect essentially refers to, is an application of Le Chatelier's principle to solubility equilibria. So over here there's two equations at work. In part B, there is the complete dissociation of soluble lead-2 nitrate, and there is the partial dissociation of lead-2 iodide, which is sparingly soluble. So when we add in lead-2 nitrate, we introduce Pb2 plus as a common ion. And when there is a large increase in the concentration of lead-2 ion, this equilibrium, this dissociation equilibrium of Pbi2, the position of equilibrium will shift to the left as predicted by Le Chatelier's principle. So we will say that the dissociation of Pbi2 into ions has been suppressed by the common ion Pb2+, which results in the solubility of Pbi2 in lead-2 nitrate solution being lower than the solubility of lead-2 iodide in pure water. Next, part D, we have water from disused lead workings which have been flooded, and we want to investigate the presence of lead-2 ions in the water by precipitating yellow lead-2 iodide. So if equal volumes of water from the flooded lead workings and this concentration of aqueous potassium iodide are mixed, calculate the minimum concentration in mole per dm cube of lead ions, which is detected in the flood water. So firstly, we mix a certain volume of this concentration of aqueous Ki with equal volume of flooded lead workings water. So essentially, when we do this, it is equivalent to a 2 times dilution, which means that the new concentration of potassium iodide is half the original value, or 2.0 times 10 to the power of negative 3 mole per dm cube. So the concentration of iodide ions is 2.0 times 10 to the power of negative 3 mole per dm cube. And for the precipitation of Pbi2 to occur, the IP, the ionic product of Pbi2, must exceed the KSP. So we are going to form an inequality and substitute in the concentration of iodide ions. And we will get that Pb2 plus Pb2 plus ion concentration after mixing must exceed 2.46 times 10 to the power of negative 3 mole per dm cube. But this concentration of lead-2 ions is after mixing, which means that to find the concentration of lead-2 ions in the original solution before mixing, again, we will need to multiply this by 2, will give us 4.92 times 10 to the power of negative 3 mole per dm cube. Part E, There are some reasons why this method of detection is not particularly reliable. So part 1, name another metal ion which may be precipitated by adding aqueous Ki. So this answer is actually in question 6, which is silver ion or Ag+. As we know, silver ion can be precipitated by adding Ki to form a yellow precipitate of Agi. Next, we are going to look at 7e part 2. When excess aqueous Ki is added to the precipitate, the complex ion PbI4 2- is formed. So explain the observations made when we add excess aqueous Ki. So firstly, we already know that PbI2 is a sparingly soluble salt. It dissociates in water to give you Pb2 plus ions and I minus ions. And for the purposes of this question, we are going to call this equilibrium 1. But when we add excess of aqueous Ki to the precipitate, there will now be a second equilibrium where Pb2 plus reacts with 4 iodide ions to be in equilibrium with this complex ion. And we're going to call this equilibrium 2. So firstly, take note that the question specifies excess of aqueous Ki. So when we add excess aqueous Ki, there is a much higher concentration of iodide ions, and this causes the position of equilibrium 2 to shift to the right to counteract the increase in concentration of iodide ions to form more of the complex ion. And when this position of equilibrium shifts to the right, it leads to the consumption of Pb2 plus. So the concentration of Pb2 plus will also decrease as well. By Le principle, this decrease in concentration of Pb2 plus over here will shift the position of equilibrium 1 to the right, and this tells us that the solubility of PbI2 has increased. So one visible observation that you're going to make is that as you add excess aqueous Ki, the precipitate of PbI2 is going to slowly dissolve. So when the concentration of Pb2 plus decreases to an extent where the ionic product of PbI2 is now smaller than the solubility product value, we will observe that the precipitate of PbI2 will redissolve. Finally, we're going to look at question 8. When aqueous ammonia is gradually added to a solution of Cu2 plus ions, it first forms a blue precipitate, which dissolves on further addition of aqueous ammonia to give a dark blue solution. And you have seen this and done this before in your QA. So firstly, when we do cation test in QA, be it by adding aqueous sodium hydroxide or by adding aqueous ammonia, the precipitates that we're looking out for are all metal hydroxides, which means that there's two reactions here. The first reaction is the formation of blue precipitate, which is copper 2 hydroxide. And secondly, the precipitate will dissolve in excess aqueous ammonia to give a dark blue solution. So we're going to answer this in the same way that we answered 7e part 2. So we're going to start with the relevant equilibria. So first equilibria is to account for how come a solution of aqueous ammonia contains some hydroxide ions, and you already know from the previous topic on acid-base equilibria that ammonia is actually a weak base. So the equilibrium we're going to write is the dissociation of ammonia in water to give you hydroxide ions, and we're going to call this equilibrium 1. The second equilibrium will be the formation of the blue precipitate. So CuOH2, which is copper 2 hydroxide, in equilibrium with its ions, so Cu2 plus and 2OH minus. We're going to call this equilibrium 2. And lastly, the formation of the dark blue solution, Cu2 plus reacting with 4NH3 to give you this complex ion, CuNH3 2 plus. You will need to know the formula of this complex ion, as well as other complex ions which are mentioned in the notes on this chapter, and we are going to call this equilibrium 3. So now that we have written these three equations, we are ready to explain. So firstly, the first aspect is the formation of the blue precipitate. So firstly, ammonia is a weak base. It undergoes partial dissociation in water to form hydroxide ions. So the presence of hydroxide ions in aqueous ammonia causes the formation of a blue copper-2 hydroxide precipitate when there is an increase in hydroxide ion concentration and the ionic product of copper-2 hydroxide exceeds the solubility product. So this first part has been accounted for. The next aspect is the dissolving of the blue precipitate in aqueous ammonia in excess to give you a dark blue solution. So when we continually add aqueous ammonia, okay, your equilibrium 3 will start to kick in and shift the position of equilibrium 3 to the right to form this complex, which is a dark blue colored solution. When Cu2 plus reacts with ammonia to form this complex ion, it leads to a decrease in the concentration of Cu2 plus. Okay, next, the decrease in Cu2 plus concentration in equilibrium 3 causes the position of equilibrium 2 to shift to the right to counteract the decrease in concentration of Cu2 plus by Le Chatelier's principle. And what you can visibly see is that the CuOH2 precipitate is starting to dissolve. And this decrease in Cu2 plus concentration reaches a point where the ionic product of CuOH2 is now smaller than the solubility product, and that is when the blue precipitate of CuOH2 has completely resolved to give you this dark blue colored solution. So with that, I'm going to end this video. Thank you for your time.